Hello everyone. Today we will going to discuss the one of the complex topic of our antenna and wave propagation system, that is Friis transmission formula. So how the power that is transmitting from the antenna is propagate into the free space with the help of pointing vector, and how we can collect the power, and what is the amount of the uh, uh, that is power received with the help of the antenna, transmitting antenna aperture and the receiving antenna aperture, and gain of the different antenna we will discuss in this topic. So one by one we will discuss each of these things. So this is the basic structure. Today what we are going to be discussed: the radio transmission communication link, field from oscillating dipole. Generally we can use this dipole antenna in most of the communication systems, and how the electric field radiated from the electromagnetic dipole, and signal to noise ratio, and antenna temperature and antenna impedance. So what is antenna aperture? How we can say that the particular antenna having this aperture? So let's suppose that power P is transmitting from the antenna, and the corresponding electric field is represented by E, and the antenna impedance is represented by Z. Then the power P is equal to E square by Z times of a particular parameter that is known as the antenna aperture AP. So this E square by Z is nothing but the pointing vector that is radiated by the antenna, and this is the aperture, effective aperture of the antenna, that a particular power that is flowing with the help of electric field pointing vector. So if we see that electric field vector in case of horn antenna, we have the aperture AP, and electric field vector is aligned in this direction, as we can see, and this is the electric field vector that is radiated or coming to the receiving antenna. Then the aperture efficiency is nothing but AE divided by AP. AP is the effective AP is the actual aperture of the antenna that is visible, and AE is the effective aperture of the antenna that is going to be receive the electrical signal that is received. How it works: as the electric field vector is superimposed on this edge of the antenna, this is a vertical metal rod that short circuit is electric field vector, and this electric field vector gone. Same is happened to this antenna, this electric field vector. So the actual size of the aperture is going to be reduced, because at the edges of the wall the electric field vector going to be short circuited. So the effective aperture is is small in compared to the actual aperture of the antenna, and it is represented by AE. And for the efficiency of a particular antenna, the effective value of the aperture to the actual value of the aperture is known as the antenna efficiency. So if we represent this thing in case of beam area, that is beam solid angle that is transmitted. So let's suppose an effective area AE represent transmitting electric field EA, and it form a beam angle of ohm A. Then at a particular distance R, it is received by the receiving antenna having the electric field vector ER. Then the power transmitting from the transmitting antenna EA by Z0 into AE, and the power received by the receiving antenna P is equal to ER square by Z0. ER is the electric field that is received from this antenna, multiplied by pointing vector R square into beam area, R square distance into this beam area. So these power are equivalent. So we may equate this power, and we find that there is a relationship, that is lambda square is equal to AE into ohm A, where ohm A is the beam area or beam efficiency. So if we put the value of this ohm A in terms of directivity, the directivity of the aperture is given by D is equal to 4 pi AE by lambda square, where A is the effective aperture of the antenna, and lambda is the wavelength over which the wave is propagating. So D is the directivity, having the another formula in terms of antenna aperture, 4 pi A by lambda square. D is also represented by, as we discussed in the previous lectures, P maximum power in one direction upon the average power. It is also represented by 4 pi divided by beam area, and it is again now this is represented by 4 pi A by lambda square. Then for properly transmitting of the antenna, for maximum power transmission, the load resistance is matched with the radiation resistance of the antenna. Then in that case, maximum amount of power is transmitting from the antenna to the free space, or it is received maximum power from the free space to the antenna if the load resistance is load resistance is matched with the radiation resistance of the antenna. Effective height. So as the aperture of the antenna is varying, its height is also varying. So let's suppose V is the voltage developed, having the antenna having effective height H and electric field it is received. Then H is equal to voltage divided by electric field, as we already discussed. So there is many antenna having different effective height. So how this antenna can work, we can see over here. So let's suppose there is an antenna having the length L by 2 and L by 2 and receive the electric field signal, as we can see over here. So this signal is received in the form of electric field wave as well, represented by E field vector. So if V is equal to H into E, then H is equal to V into E. So now the relationship between the effective height of the antenna and the aperture of the antenna. Let's suppose the power is P is transmitted by the antenna having voltage V and radiation resistance R. So 1 by 4 V square upon radiation resistance, and we have already discussed V is equal to H square E square by 4R. P is equal to SAE, that is E square AE by lambda square. Then effective height we can easily calculate by this formula. Effective height is equal to twice of under root of RR upon AE by Z naught, or AE is equal to H square Z naught upon 4RR. So this we can see how the effective height or the radiation effective height and effective aperture are related with the antenna. Now consider an example. Let's suppose an element L is equal to lambda by 2, and this element having a current distribution that is 2 divided by pi, that is 0.04 of the maximum value. So the effective distribution of the current is like this, as we can see over here, and it is having the maximum value 1, but average value is 0.64. In case of if the antenna height is very small, like 0.1 lambda, it is almost triangular in shape, as we can see over here. So the effective height is nothing but the average value of the current to the maximum value of the current into effective height of the physical height of the antenna. Now the fringe transmission formula. So how this fringe transmission formula works? Let's suppose we have a transmitter antenna T having the effective transmitting area AET and effective power PT, and at a distance R from this antenna we have a receiving antenna AER, and it can receive the power PR. It is having the gain GT and it is having the gain GR, and this distance is R. So how we can transmit? Let's suppose if we replace this antenna by an isotropic source that can radiate the power in all the direction. So the total power PT is transmitted over the complete sphere, that is, so average power that is radiated from that receiver that this transmitter is 4 pi into R square, that is power radiated over the complete 4 pi square. So SR, that is pointing vector, that is power radiated by the isotropic source, power in divided by 4 pi square over the complete sphere. Now if we convert this antenna into a directional antenna that having the gain in that particular direction, then that power is multiplied by the gain of the antenna. Now the pointing vector became SR is equal to PT GT upon 4 pi R square. Now this pointing vector is traveling like this into the free space, and a small portion is captured by this receiving antenna. So the amount that is received by the receiving antenna is multiplied by the effective aperture of the receiving antenna as well. So power transmitted PR, that is power traveling in the space, that is PR, and power received is equal to pointing vector multiplied by the effective aperture of the receiving antenna. So So the total power received by the receiving antenna is PT GT AER upon 4 pi R square. Now we already know, as we discussed in the previous previous slide, that GT or D is equal to 4 pi AE by lambda square, and if we replace D by G, as D is related to G with the help of efficiency. So if we consider that efficiency is 1, the antenna is very effectively 100% efficient, then this D is converted into the G, where G is the gain of the receiving or transmitting antenna. So GT is equal to 4 pi AET by lambda square. So we can replace this GT by 4 pi AET by lambda square. We have the power received by the receiving antenna in terms of effective aperture of the receiving and transmitting antenna is equal to PR is equal to AER AET into PT divided by R square lambda square. So this is the fringe transmission formula that is highly dependent upon the effective aperture area of the transmitting and receiving antenna, as well as the distance between the antenna and over the frequency over which the antenna is going to be used. We can convert this transmitting antenna, this fringe transmission formula, in terms of gain of the transmitting and receiving antenna, because gain is highly dependent upon AET and AER. So we can convert this formula in this formula as well, that is power received PR by the receiving antenna is nothing but PT, that is the gain of the transmitting antenna, PR, that is the GR, that is the gain of the receiving antenna, into PT, that is power actually transmitted, divided by 4 pi lambda by R square. So this 4 pi lambda by R square is nothing but the total transmission losses that is faced by this transmitting power, that is from the wave from the transmitting antenna to the receiving antenna. So this part is known as the transmission losses, and this total formula is known as the fringe transmission formula, where power received is equal to PT GT GR divided by 4 pi lambda upon 4 pi R by lambda square. This is R, this is lambda, 4 pi R by lambda square. So in this way, by knowing the gain of the transmitting and the receiving antenna and the power transmitted or the power received, we can find out the power received by the receiving antenna or power transmitting by the transmitting antenna, as well as we can calculate the operating frequency and distance between the antenna if all the another parameter are known to us. Then the field from oscillating dipole. So generally this is oscillating, that is dipole is one of the famous antenna that is used in most of the places where having the radiation pattern of omnidirectional. As we can see, the omnidirectional radiation pattern is nothing but, if this is the antenna, the radiation is in this direction and in this direction, and there is no radiation in this and this direction, and in Beke omnidirectional, that is in the plane where the antenna is standing. In that plane, the radiation is uniform and make a donut type structure. So this is the having radiation, this is the place where maximum radiation is there. Then how we can see that this oscillating dipole can transmit the power, as we can see over here. So the field is only radiated when the charge is moving with a uniform velocity along a straight conductor and does not radiate. So if the charge is moving uniform velocity, there is no radiation. But as the charge is moving in the direction like a oscillating motion or harmonic motion, like the charge is accelerating and then deaccelerated, then again accelerated. So the velocity continuously change with respect to time, and this create a radiation in a fixed length of the antenna, that is lambda by 2. So in this way a antenna can radiate the radiation. So as we can see, there is a negative charge electron and a positive charge hole, and if we apply the voltage across this terminal, the electron start moving in this direction, holes start moving in this direction, and they accelerates. As it crosses each other, as it approaches each other, we have a particular direction of the current that is moving from this direction to this direction. And if we see the field field line that is radiated by this charge are coming from positive charge to negative charge, as we can see over here. When these charge approaches each other, this radiation make a shape like this, and at a certain point when they cross each other, this loop became complex over here and cut each other. These lines are cut each other over here, and it can cut it out from there and radiate it into the space at a t is equal to 1.4. So this is known as the radiation that is coming from the antenna when the electric field line from the negative charge, from the positive charge to the negative charge are cut by each other and radiated into the space is known as the radiation. Then the radiation is coming from now positive to negative and again form this like structure. So in this way, electric field radiated from the fixed length dipole antenna into the space. So the direction is always perpendicular to the plane of the antenna. That's why it makes a donut type structure. So as we can see, this is the representation of the electric dipole antenna and the radiation that is coming from the antenna, as we can see over here. This is the electric field direction, and the corresponding magnetic field are in the plane that is 90 degree to the electric field plane. So if this is the electric field plane, this is the magnetic field plane, and we have the radiation in the magnetic field as well. So the electromagnetic radiation is composed of both the components. We will discuss electric field again and again over here, but the similar behavior is produced by the magnetic field as well. The only difference is that the field is 90 degree with respect to the electric field, almost having the same behavior. So if we see the electric field radiation in this direction, we have the magnetic field direction in the xy plane or in the plane that is horizontal to the transmitting antenna. So this is the actual simulation of the radiation that is coming from the antenna. So this is the point where the antenna is start radiating the radiation, and the radiation is going out and out from the transmitting antenna. So this is almost spherical near the antenna, but as it approaches away, the wavefront became more and more flatter, and when the distance became few hundred kilometers or few thousand kilometers, the wavefront became almost constant. So when a small antenna is received, the amount of the power is almost flat. There is no variation in the radiation. So in this way, we have the electric field radiation. Now signal to noise ratio. Whenever a signal is transmitted, there is some signal having the noise as well that is added to the signal. So the signal to noise ratio is one of the very important parameter that can find are we able to reconstruct the signal or not. The signal power to the noise power ratio is known as the signal to noise ratio. So whenever this signal to noise ratio became greater than 1, we can easily find the signal, but it is destroyed, like noise power became very large in compared to the signal power, then we cannot able to restore the signal. So signal to noise ratio in compared to a device, if we have a signal to noise ratio at the input and if we have the signal to noise ratio at the output, so the ratio of these two signal to noise ratio is known as the noise figure of the device. So if the device is very noisy, it produces more noise compared to the signal. So the signal to noise ratio at the denominator increases, so the noise figure became down. So if a device is very noisy, the noise figure became down and down, and it can produce more noise compared to the signal power. So we can easily by just checking the noise figure, we can easily find out that the device is noisy or not. So thank you for this lecture in which we will discuss different radiation from the transmitting dipole, Friis transmission formula, and in the last signal to noise ratio. Thank you.